Now let's talk about inverse functions. Please don't let these confuse you. Just always go back to your definitions and look at the way we've solved them. Now write this down. The definition of an inverse function is a function, let me get to my pen here, is a function g such that f of g of x is always equal to x for every x that's in the domain. And g of f of x is equal to x for each x in the domain of f. And we tend to not want to write g's and f's, but we use f negative 1 as the inverse of f, or f inverse. So the trick here is when I apply f to its inverse, I get x. When I apply the inverse to f, I get x as well. So clearly, they're inverses of each other. So let's verify these two are indeed inverses. So how are we going to do that? Well, let's see if f of g of x, let's see what that equals. So everywhere in f I have x, I'm going to plug in this g of x thing. So this is 2 times, now this is the cubed root of x plus 1 divided by 2 cubed minus 1. So let's see what I get here. This is 2. These undo each other, and that's a pretty good sign that you're heading in the right direction. X plus 1 over 2 minus 1. So that's, what do you know? X plus 1 minus 1 is equal to x. We're not done. We have to show that g of f of x is also equal to x. So g of f of x is equal to, let's see, the cubed root of x. So that's 2x cubed minus 1 plus 1 divided by 2. Well, so this is the cubed root of, let's see, those cancel. 2x cubed divided by 2, cancel. So it's a cubed root of x cubed, or x. So they're inverses of each other. Let's look at the reflexive property of inverse functions. Suppose I have a graph of f that contains the point AB. All right. Then the inverse of the function, first of all, can be reflected about y equals x. And the inverse function contains the point BA. So if f of x contains AB, the inverse contains BA. Now, try this problem. Turn the video back on when you're done. Now let's look to see if an inverse actually exists, because if it doesn't exist, it's kind of worthless continuing. A function has an inverse if and only if it's 1 to 1. And obviously this is not 1 to 1. And if f is strictly monotonic on its entire domain, then it's 1 to 1 and therefore has an inverse function. All right, let's look at these two functions. Does an inverse exist? Well, let's see if they're monotonic. The easiest way is to take the first derivative. So this is 3x squared plus 1. Now this is always positive, so this is monotonic. So yes, there does exist an inverse. Now I'm just looking for the existence, I'm not trying to find it. Let's look at this one. F prime of x is 3x squared minus 1. And this can equal 0. This can be negative. This can be positive. So there does not exist an inverse. This is not monotonic. This one is monotonic. No matter where I draw this line, I'm only going to cross the curve once. Here I'm going to cross it Up to 3 times. All right, give it a go. Turn the video back on when you're done. All right, now here are some guidelines for finding an inverse function. We've been just showing existence. All right, first of all, determine whether it has an inverse. Kind of silly to go on if it doesn't even have an inverse. Now, solve for x as a function of y. Then swap x and y, and this is your inverse function. Define your domain of your inverse to be the range of your function, and then verify. So there are 5 steps. Let's find the inverse of this function right here. F of x is equal to the square root of 2x minus 3. All right, if we look at this, I can just analyze for x greater than 2/3. So basically where this function is defined, it is monotonic and increasing. I can do the derivative, but I'm really being kind of lazy. I can draw my diagram and do it. All right. So now I want to solve this. Y equals the square root of 2x minus 3. Next, I want to solve this for y. So y squared is 2x minus 3. Excuse me, I want to solve it for x. So x is equal to y squared minus 3 divided by 2. Okay, so now I've done the solve. Here I've done the show. It's monotonic. Now I want to interchange x and y. So y is equal to x squared minus 3 over 2. So now we're going to interchange x and y. All right. And now I'm going to replace y with f inverse. Y with f inverse. All right, now we need to find the domain of f inverse, which is a range of f. So this is from 0 to positive infinity is my domain. All right, and we can verify this. F of f inverse is equal to, okay, so this is going to be the square root of 2. Now my inverse is x squared minus 3 divided by 2. Minus 3. So this is the square root. Those go away. So I'm going to have x cubed minus 3. X squared minus, let me rewrite it. Did I do that right? No, I didn't. Guys, you can't let me make these mistakes. Okay, so that's plus x squared plus 3 minus 3. So this is the square root of x squared, or x. Now f of g inverse is, or f, oh goodness gracious, f inverse of f is, okay, so I'm going to start with my inverse function, and that's x squared. So it's going to be the square root of 2x minus 3 squared plus 3 divided by 2 is 2x minus 3 plus 3 divided by 2, and lo and behold, yes, that is x. All right. So I found my inverse function. We're done. You give this one a go. Make sure you verify everything. Now, if f of x is sine of x, where is it 1 to 1? Well, clearly, it's only going to be 1 to 1 in this area right here, or from negative pi over 2 to pi over 2. Everywhere else, it's not 1 to 1. So we know f is increasing monotonically from this region. Now, could we have switched over and gone from pi over 2 over? Yes, we could have. All right, let's look at this region. F prime of x is cosine of x. And it turns out cosine of x is also positive in this region. All right. So we have to be very careful when we look at trig functions and make sure that we're selecting a region where they're monotonic and either increasing or decreasing. So what would f inverse be here? All right, just solving this. Y is sine of x. So x is the inverse sine of y. So my inverse function would be inverse sine of x. Not very attractive. Now, you try this one. Stop the tape when you're done.